So welcome to part 2 of lecture 5. So I left off part 1 by stating this theorem here and explaining that in order to prove it, we have to check that all three conditions of a subspace are satisfied by the span of V1 through Vm. And I've already worked out the first condition, checking whether that 0 belongs to this set. So let's do the other two conditions. So first of all, let's take two arbitrary elements inside of the span V1 through Vm. And our goal is to now show that this the sum of these two guys is also inside of the span. Okay, so now let's just write out what it means to be in here. All right, so we know that x looks like a1 times v1 up to am times vm, and y looks like b1 times v1 up to some constant bm times vm. So then let's just add these two guys together. So then x plus y is equal to a1 b1 up to am vm plus b1 v1 up to bm vm, where you can use the properties of a vector space to kind of regroup the terms because addition commutes. So we have here that we have a1 v1 plus b1 v1 in the first spot, and then we can go all the way down to am vm plus bm vm. So what we're going to be doing, right, is just grouping all the coefficients of v1 together. So the coefficient of v1 is a1 plus b1 all the way down to am plus bm times the vector vm. But now the way that I've written it is that each of these ai plus bi's, right, this a1 plus b1, a2 plus b2, those are all just scalars. So now I've written x plus y as a scalar times v1, a scalar times v2, and so on. So that just means that x plus y is in the span of v1 through vm. Okay, so we've checked off the second condition of being a subspace because it's closed under addition, and now closed under scalar multiplication is proved kind of in the same sort of way. Right? We take some element x inside of the span of v1 through vm, and so we know that x then looks like a1 times x looks like a1 times v1 up to am times vm, and then we multiply it by any scalar. So let c be some scalar. Then cx is equal to c times a1 times v1 up to am times vm. We use our distributive property for vector spaces, so you can regroup all of this as c times a1 times v1 up to c times am times vm. And you notice that this last guy right here is a linear combination of v1 through vm, so cx is also in the span of v1 through vm. So thus span of v1 through vm is a subspace because we've shown that it satisfies the three criterion for being a subspace. So here we've proved off condition A that the span of any vectors is a subspace of the vector space. But what about the second condition? Okay, about span v1 through vm is the smallest subspace of V to contain the vectors v1 through vm. Well, I started the proof over here. So suppose that W is a subspace that contains v1 through vm. And the way that the proof works, let me just move it over here, is to say that if v1 through vm belong to W, then the span also belongs to W. Okay, and I will explain why that's the case. Right? So then for any elements a1 through am in F, we have that a1 times v1 plus a2 times v2 up to am times vm is inside of W, right? And this just follows from the fact that W is a subspace. So we're just using the fact that W is a subspace to say each of these scalar multiples would be in there, and then you could sum them up, and you still get something inside of W. But this just means that any linear combination of the VI's is in W's. So this means that span of V1 through Vm is a subset of W. Okay, so if a subspace contains V1 through Vm, then it also has to contain the span. Now, important terminology is given in the next definition. We say that if the span of your vectors, V1 through Vm, is actually equal to the whole space V, we say that V1 up to Vm span V. Okay, so these M vectors are enough to get all the elements of V. And you would have seen this in Math 1B03. And let me just kind of remind you kind of for the special example. If we take V to be R2, kind of think of the plane, and if we take the first vector to be 1, 0, and we take our second vector to be 0, 1, then the span of those two vectors is by definition all scalar multiples of the first vector plus all scalar multiples of the second vector, where A and B are allowed to run through R. But notice that when I take this guy here, right, I get the vector A0, and over here I get the vector 0b. So this is the same thing as all vectors of the form AB, where A and B are allowed to run through R, but this is just R2. Okay, so these two vectors here span R2, and you probably remember from Math 1B03 that we would call these the standard basis elements, right? So these are the standard basis elements. So the word basis will come up later on in this course. And in fact, what I just wrote here generalizes, right? Because you can take 1, 0, 0, 0, and then the vector with 1 in the second spot and zeros everywhere else, the vector with 1 in the third spot and zeros everywhere else, all the way down to 1 in the last spot. These collection of vectors span Fn. Okay, so it doesn't even have to be the real numbers necessarily, it could be the complex of numbers. So now that we know what it means to span a collection of vectors to span a vector space, we can talk about a vector space being finite dimensional. And what it means for a vector space to be finite dimensional, it just means that if there's some collection, a finite collection of objects, V1 through Vm, such that they span the whole space. Okay, so you can find a finite list of elements, V1 through Vm, that span the whole set. So, and when that's the case, we say that V is finite dimensional. So based upon what I just wrote there on the previous page about Fn, we get that Fn is finite dimensional. Because, and why is that? Well, we have found a collection of vectors. We have n vectors here that their span is all of Fn, right? So that means Fn is finite dimensional, and we say that a vector space is infinite dimensional if it is not finite dimensional. So in the next two parts of my lecture for today, we're actually going to look at some vector spaces that are infinite dimensional, and I will explain how to prove that something is not finite dimensional. So that's what I wanted to say for this part of the lecture. I'll see you in the next part of the lecture where we're going to talk about vector spaces and polynomials.